So I'm going to talk to you today about the open memory interface as a path to higher bandwidth, higher capacity near memory. So before we get started, though, and I did this in conjunction with a colleague named Jim Handy from Objective Analysis. I'm Tom Coffin of Coffin Associates. Before we get started, I want to make clear what I'm talking about when I say near memory. So this is a representation of a memory storage hierarchy. It's actually a chart that Jim has shown many times. It shows roughly where each memory type fits based upon its cost versus its performance, as measured in price per gigabyte and bandwidth on the two axes. It's a log plot. Each of these orbs has its own latency, and this shows typical numbers for these different latencies. The DRAM that is attached directly to the processor is named near memory. There's currently a lot of interest in adding even more DRAM and perhaps 3D crosspoint or Optane memory and other technologies in the memory port pools via any of the number of interfaces, which include, for instance, SMP, OpenCAPI, Inception, CXL, C6, Gen Z, and even PCIe and Ethernet. These we will call far memory. They're a higher latency memory. The focus of this presentation is what we're calling near memory, specifically DDR, high bandwidth memory, HBM, and also OMI, this open memory interface. So with that in mind, I'm going to discuss the need for more near memory bandwidth and also memory capacity. I'll follow with some real world examples of the three current near memory interfaces, that is DDR, high bandwidth memory, and OMI. And after that, an explanation of how an OMI differential DIM works. I will show how it can support the simultaneous use for a variety of near memory types. Carl Rupp compiled statistics for the entire history of microprocessor chips from 1973 through today. You can download it from the website. The URL is shown there. So we drew trends for the three data series in this database: transistor count, clock speed, and also core count. While transistor count has increased at a steady rate, clock speeds leveled off in the early 2000s. To counter this, designers started multiplying the number of cores to allow performance to continue to increase. And that has driven a need for improved memory bandwidth. The standard approach to bandwidth improvements has been to focus on accelerating the speed of the DRAM interface, both through refinements of the protocol from DDR through DDR5, and also the bus clock speed itself. The drawback to this is that capacitive loads limit the frequency of the bus signals. The number of DIMMs that a channel can support keeps shrinking as the bandwidth requirements increase. A common approach to this is to add memory channels, but this comes with its own set of issues. When you add memory channels to a processor, it adds die cost and burns also a lot of power. Consider that a LR DIMM channel requires some 152 processor pins. 6 channels almost gets you to 1,000 pins, consuming a lot of the most expensive silicon real estate in the system. Meanwhile, each of these pins represents a capacitive load that burns power while being driven at high frequencies. That has been a concern for some time. It has been addressed to some degree with changes to the DIMM architecture. DDR4 is the current mainstream memory, and that makes it inexpensive. HBM, high bandwidth memory, costs significantly more, but its 1,000-bit bus boosts bandwidth enormously. OMI, this open memory interface, is new. It's based upon standard DDR differential or DDR DRAM chips, and it provides very large memories at speeds that can rival the high bandwidth memory. IBM uses the open memory interface in its Power 10 processors to reduce the processing area consumed by IOs while still achieving a high data bandwidth. The OMI memory channel leverages industry standard 32 gigabit per second PHY signaling, but unlike PCIe, the protocol has been optimized for ultra-low latency memory interactions. The 16 OMI channels called out in this photo each consume only 2.2 millimeters of die area while supporting 64 gigabytes per second of bandwidth. With 16 of these channels then, the chip has a terabit per second of available bandwidth to the memory. Since the channels are only 2.2 millimeters square, OMI provides a processor with 2.9 gigabytes per second for each square millimeter of die area. In addition, OMI provides up to 256 gigabytes per channel, useful for applications such as machine learning and other big data applications. With, the differential DIM uses the same proven differential signaling that's behind PCIe and Ethernet to offer high bandwidth type high bandwidth memory like bandwidth, while also using about 1/4 as many pins as a DDR. Since the DRAM signals are now produced on the differential DIM by the controller, they can be much shorter than they can be on the motherboard, and therefore consume less power. Since a controller replaces the buffers on the LRDIMM, it adds much less than 4 nanoseconds to the DIMM's latency, so it's a very small latency penalty. The controller itself is not a large chip, so it's not expected to add all that much to the cost of the differential DIM. Future versions will not only be able to support enhanced functionality, but will also allow a processor to communicate through OMI with a variety of memory types. Here we have a Power 10 processor connected to 8 OMI DIMMs, differential DIMMs, one for each channel on that side of the processor. OMI is an alternative to DDR. It's similar to CXL in that it can hide the differences between different memory types. But OMI works for near memory, while CXL is a solution for far memory problems. What will we attach to this Power processor's OMI channels? Well, DDR4 is today's obvious choice, but there's no reason we couldn't add DDR5 later on, once DDR5 prices drop below those of DDR4. Through the OMI channel, these will look the same. In fact, you could make a differential DIM with LP DDR and have all three running on the system at the same time. But there are other possibilities too. Just as you can run several different DRAM types in the same system. Oh, got it. You can add another memory type, say 3D Crosspoint, to the system. But it doesn't stop there. A single system could have a different memory type on each and every OMI channel without the processor needing to worry about the differences between any of them. So OMI can give us near HBM bandwidth at larger capacities than DDR. That's illustrated in this chart, where the bandwidth appears along the bottom axis and the capacity shows on the vertical axis. So in conclusion, higher core counts require higher near memory bandwidth, and HBM offers that, but at the cost of limited memory size because of the limitation on the number of chips that you can have. But modern software requires an ever-increasing near memory size. And although DDR can do that, it's significantly slower than HBM and OMI. Systems need near memories that can provide both high capacity and higher performance. OMI does this while consuming less processor die area than DDR or HBM. And as an added bonus, OMI can be useful for future systems with a mix of memory types. So higher core count requires higher near memory bandwidth. And near the bottom of, note the location here. So the call of action is there's an OMI booth that's on the floor there. And you can see where the location is there. And go there, you can see examples of these differential DIM memory devices, and also get a chance to talk to people about OMI. With that, here's some references, and I thank you. And is there time for questions?
We have time for questions.
Okay.
Do you have any updates or insight in terms of the throughput that you can get in the DDIM with the DDR5? I know I think you're a little bit still bandwidth limited with DDR4 on the OMI DIM.
Oh, okay. You're talking about for the DIM, yeah.
Yeah. So in the OMI interface, you have 28 gig SerDes that are going there.
Mm-hmm.
I was just wondering if you had any insight on, when we're going to hit the bandwidth capability with DDR5 on a module to take advantage of the speed.
Sure. So actually, our next speaker is going to talk more about that, and I think he can probably answer that question.